So welcome back for afternoon talk. Without further ado, kicking us off from Tel Aviv University, we have Lior Bary Soroker, who will speak to us today on probabilistic Galois theory, the square discriminant case. Lior.
It's okay. Now you hear me? Should I repeat or it was recorded? Okay. Yeah, and it was with Zev, and this was amazing. It was I learned that you shouldn't, when you organize something, you have to make sure that the audience is the #1 priority. And also I learned later, because this was my first mathematical event, that it's highly non-trivial. Many people just try to be polite, and the price is the audience pay the price. So thank you. I learned a lot of things in that. Today I want to talk about probabilistic Galois theory. Sorry about the typo. And maybe it's not the main topic of interest in analytic number theory, but it relates. And I want to address some kind of the fundamentals of Galois theory, but maybe let me start with what is Galois theory. So in Galois theory, we have a polynomial with integer coefficients, and it has complex roots. And we want to know what can we say about the arithmetics of the roots from the coefficients. And Galois had this great idea that he said, let's look on the group of automorphism of the splitting field, that is the minimal field that is generated by the roots, together with the action on the roots, so as a subgroup of Sn, and this group encodes the arithmetics. So for example, f has a rational root if and only if the group has a fixed point. F is irreducible if and only if the group is transitive. The discriminant of f is a square, non-zero square, if and only if the Galois group is contained in AN. So you can read the arithmetic information from the group. And maybe in application, the most important thing is the direct Galois problem. What is the direct Galois problem? The application gives you a polynomial, and you need to say what is the Galois group. So you need to compute the group. And there are many applications. Maybe the most familiar for whoever was here yesterday is the result of Dartige and Maynard, that we saw that they need certain type of Galois group in order for their result to be applied. Okay, so if you've been here yesterday, it was in the second talk. And I want to address maybe a naive question, which is the opposite of the direct Galois problem. And to motivate this question, I found this quote by Carl Sagan, that questions are good, essentially, right? Even if they look a bit naive or stupid at first glance. And this naive question is a try to understand the Galois-theoretic world. And it's a question that I think everyone in the first course in Galois theory, it's a question that immediately comes to mind. And the question is the opposite to the direct Galois problem. It's given a group G, finite group G, can we realize it as the Galois group of a polynomial with integer coefficients? This group, I think Galois probably thought about, many people thought about this question, sorry. But it's still open, and this is something that is unique to mathematics, right? That we have questions that are for ages open, and it's called the inverse Galois problem. And the motivation for the question is important because it's a sync problem. Namely, it's a problem that interests enough people that they develop machinery and tools to study it. And for example, the tools that were developed for the inverse Galois problem were very useful in the direct Galois problems, the same kind of machinery. The question of this talk is to understand why this problem, which seems so naive, is so difficult. So I want to understand why the problem is. It's not a probabilistic problem, but I do think that if we think about it as a probabilistic problem, we get new insight. So I take a probabilistic point of view. Mike, is it okay now? So I fixed it during, thank you. And I take the simplest model of randomicity. It's called the large box model. So in this model, we choose the coefficients in a box. I mean, we fix the degree, and we have n coefficients. I always like work with monic polynomials. It's not necessary. And we choose the coefficient from a box as integers in a box, and we let the size of the box grow. Okay, it's the simplest model of randomicity that we have. If we choose the polynomial random in this way, then the Galois group becomes a random Galois group of Sn. And the question that I'm after is how the Galois group distributes as a Galois group of Sn when I choose the polynomial at random. And the first result is a result of van der Waerden that says that asymptotically, almost surely, the Galois group will be always Sn. So we really look on the standard deviation. We're looking on events that goes to 0 if we want to understand how it distributes. Okay, so this is the result from 36, and back then he also addressed the question: what is the second most probable group? And he made a conjecture that the second most probable group is Sn minus 1. So polynomials that have a root. Here is a translation. The Galois group is Sn minus 1 is similar to say that the Galois group, that the polynomial has a root, and this tends to have the same probability as for the polynomial to be irreducible, and this is a probability that it's pretty easy to compute. It's some explicit constant c depending on n, Cn, times 1 over h. Okay, so fixed point correspond to a root. And so the probability that the Galois group is Sn minus 1 is the same as having a root, and what left is generic, like in van der Waerden theorem. So this is the van der Waerden conjecture. And since the probabilities are difficult to compute, I think that we should address some numerics. This is a picture of myself doing numerics. It doesn't work well, but luckily I found 2 students that are young and they are really good at computers. And we did some numeric with Lior Bary and Noam Pirani, and I kind of think that there should be a power law for the probability. So I plot everything in logarithmic scale, both h and the probability, to capture the power. Now this is the first thing: is the probability to be Sn, and it should go to 1. So it means that the log should go to 0. And in fact, for all the numerics are in degree 4. And for degree 4, we have a result. We know that indeed the van der Waerden conjecture is true. So those dots are what we are expecting from theory. Here the theory is actually theorem, and the yellow points is what we see in experiments. And maybe it's interesting to say that how much time it takes to compute that. So I prepared it because I don't remember by heart. So the first point, it took the first point, everything is a random algorithm. So the first point, it took 11 seconds. This is height 100. And we took something like 8 million polynomials to compute it. And the last point, for example, took 19 hours to compute. And it was 112 billion polynomials that we needed to compute the Galois groups. And this is only for Sn. The next group, what should be the next transitive group coming after Sn? Someone want to guess? I didn't hear you. I heard that someone says something. What is the next group? It's the group that appeared yesterday, D4. So the next most transitive probable group according to the numeric is D4. And here is again, the yellows are the actual experiment, and the orange is what we expect from theory. And here we have in the same paper of Chow and Dittman, we know that up to a constant, it should be the probability should be h to the minus 2 log h squared. And we see that in the log scale, up to a constant is a translation on the y-axis, right? So we see that the constant converge quite quick, and we can compute the constant from the experiment. Okay, the next group is, here we don't have theory, so we just guess. So the next group is the alternating group. So I don't know if it convinced you, but I drew the actual probabilities from our random algorithm, and I compare it to square root of h. The problem is that H goes up to 10,000. And the problem is that when you are at around 10,000, log square, for example, seems bigger than square root of H. So you need to go much farther in the algorithm in order to distinguish between powers and logs. So this is AN, and we see that it's relatively up to a constant like square root of H. The last group is the Klein group that also appeared in yesterday's talk. And here I want to say that I can compare it with this. This means that it will be the same as D4, but divided by square root of H, and this is what we expect. And maybe I should stress it even further. So for the last point, we had 112 billion polynomials about, and out of this 112 billion polynomials, out of this there were something like 30 AN polynomials, A4 polynomials. So out of 112 billion, there was something like 30. So I don't know, but it's really drastic. What? No, it's impossible. It's too large. So we do a random algorithm, and we do some kind of sieving at the beginning, so it will run. Because if you have a lot of memory, you can sieve small primes, and this really accelerated the procedure. Okay, so this is the numerics that give you some feeling, and this is for degree 4. The interesting degree are bigger, but our algorithm becomes much slowly. Let me give you some historical background for bounds on the Galois group B in Sn. So in 36, it was van der Waerden result and conjecture that I mentioned before. In 1956, I think this was the first power-saving result by Knobloch. And then in 73, Gallagher introduced the large sieve in order to get a square root saving up to an epsilon. And this epsilon was removed in 2010. So in 2010, we had that the probability is smaller than h to the minus. And then in 2013, completely different method, something which is has a very bad dependence on n, but very good dependence on height, or better dependence on height from previous result, was a result by Dietmann that used some kind of method from integral points on surfaces in order to bound this probability to -2 plus square root of 2. This is a number that should be bigger than 0.5, if I wrote it correctly. It should be something like square root of 2 is something like 1.4, right? So it should be okay. I think I didn't mess it up. And then there was some quiet, and it's interesting in probably it's something that is very common in the history of science. In 2021, there were 3 new results. Each one made a significant improvement on the previous world record by 3 different groups. One is Dietmann and Chow. The other is Gaffney, Lemke, Oliver, Lowry, Duda, Shaken, and Zhang. And the other is by Bhargava. And let me describe what happened there, at least the last one. What happened? So you remember the van der Waerden conjecture is that the second most probable group is Sn minus 1. And we have a really explicit asymptotic for this in order to prove that this is the second most probable group. And a weak van der Waerden conjecture is just saying that this probability is the same order of magnitude. It still doesn't answer the question, what is the second most probable group? But we know that we cannot do better than this, right? Just to compute the asymptotic. And this is what Bhargava really proved, that the order of magnitude is correct. And in fact, he proved something much more precise. He proved 2 results. The first result, he proved that the Galois group is the second most probable group is either Sn minus 1 or An, up to some very explicit error term, which is the order of magnitude to be Sn minus 2, by the way. So we cannot do better than this. And he proved that the probability for the Galois group to be An is of order of magnitude of 1 over h. And in fact, if the way I see it, this is the main innovation. This is what people couldn't do before. And along the year, the bounding the probability for An in all results around the probabilistic Galois, random polynomials were around this problem. This somehow is the most difficult problem. And I want to tell you a little bit my insight on this problem. This is what I'm trying to do. So how small is the probability that the Galois group is AN? Let's start with the naive heuristic. The naive heuristic is, so this is just a reminder of what we talked so far. So the best result is h to the minus 1. Heuristic might suggest that it's h to the minus n over 2. The difference is drastic. I mean, the really h to the minus n over 2 is very, very small number. And the naive heuristic suggests that the probability is even smaller. It's h to the minus n minus 1. And let me prove you the naive heuristic, okay? So because it's a very simple, simple-minded argument. So the first heuristic assumption is that the probability that the Galois group is AN is the same as the probability of the discriminant to be a square. Chantal say yes, which is good. Remind me this in 2 or 3 slides. But do you know to prove it? Okay, good. I mean, it was better if you could. But so this is something that I think is correct, but I don't think anyone has any way to prove it at the moment, or anyone is close to it. I wish I was wrong. So this is a fairly good heuristic assumption. The second assumption, the second thing is to notice that the discriminant is a polynomial. My polynomial is monic, so the discriminant is a polynomial in the coefficient of degree 2n minus 2. So when I plug here numbers around h, I will get something which is roughly around h to the 2n minus 2. Agreed? This is okay also. I don't think this is a problem. And the last assumption, which is a bit far-fetched, is we don't know anything about the discriminant except that the discriminant always is 1 or 0 mod 4. It cannot be 3 or 2. So except this, we don't know nothing. And we have a large enough number that we don't know nothing. I think that I learned it in 2005. If you have some number that you don't know nothing about, you expect that it will be random. So a random number of this size, the probability to be a square is h to the minus n minus 1. And this is the naive heuristic. And what I want to show you today that it's completely wrong. The naive heuristic is false because there are many non-trivial symmetries. Last step is wrong. The 2 others seems to me very reasonable, but the last step is completely wrong. So let me give you lower bound for the probability to be AN, and I want to show you the symmetries. This is a work that I did with PhD student Ben Porat and former postdoc Vlad Matei. We show that the probability is at least h to the minus 3 over 4n. And the idea of the proof is very, very simple. I take n 0 mod 4 just for simplicity. And then I just take polynomials that satisfy this equation. So I'm taking polynomials such f plus f prime is a square. Okay, this is a simple symmetry. Why they are so good? Because I can use the resultant formula for the discriminant. So the discriminant of the polynomial is the resultant of f and f prime. Usually there is minus 1 to some sign, but this is why I took n equals 0 mod 4 to ignore all sign changes. And the point is that resultant, if you look on the formula according to the roots, then it behaves like GCD. I can add one of the variables to the other. It's very similar. So the resultant of f and f prime is the same as the resultant of f and f plus f prime, which is the same as the resultant of f and g square. And again, the resultant is multiplicative, so it's the same as the resultant of fg square. So the discriminant of any polynomial of this form is a square. And you need to work a little bit harder to show that almost surely the Galois group is really the alternating group. Some extra work, okay? And if you want to count, and I want that f will be of size h, then I need to take g of size of a height square root of h, and I have h to the quarter many polynomials like this. So the count is pretty easy. And of course, for every g, there is unique f because this is diagonal metric. And if there is question for you, no, you need to speak up. I don't hear you. Yeah, sure, but it will not change that. Yeah, indeed, you can take other linear forms, but it will not contribute. It will contribute to the constant. It will not give you a higher order of magnitude. I mean, at least we tried it, and we don't really work with this symmetry. Just a nice. Okay, what do you do when you have? No, it's just what we found and what anyone found. Yeah, there should be more. I don't think this is just what we found, but I believe that it's just because this is what we found. And in fact, when I was young and I would find something nice, I would think that I'm smart. But when I'm old, I know that if I find something nice, I need to look in the literature who found it before me, right? It's too simple to be new, right? This symmetry. And okay, first I found a paper of Landesman, Lemke, Oliver, and Thorne, who used similar symmetries to get some bounds on the counting of AN number theory. But as they noticed, I'm too far. As they noticed, Hilbert already found symmetries of this form. And Hilbert, if you use Google Translate on his paper, or if you know German, said that he learned it from Hurwitz. So even Hilbert was not the first. So it goes back a long while, but and to the best of my knowledge, this is the only type of symmetries that exist, that people know of. But certainly I don't believe that these are all. Okay, because Chantal was doing like this, I will talk about square discriminant. So we all agreed that square discriminant polynomials should have Galois group AN, at least typically. So what can we say about this? So this is kind of a conjecture that I don't know how to prove, but we can compute that this probability is much larger than what we saw before. This is h to the minus n/2 minus a half, which is much larger than what we saw before. And here also this is the comparison with what we had before. And here the proof is very simple. This is the only proof in the talk. You take a polynomial g, which is generic, namely the coefficient are any number between minus h and h, and you plug inside it x squared. Okay, so you get this kind of polynomial that you have only even terms. And for this polynomial, one can easily prove that the discriminant is a square if and only if the free coefficient is a square coefficient. Okay? This is something that you can compute using Galois theory quite easily. And therefore, the probability that this discriminant is a square is the same as the probability that the free coefficient is a square, and all the odd coefficients are 0. So you get h to the correct number. But the drawback is that in this family, none of the groups are AN. So I got a much bigger family. All have square discriminant and none have Galois group AN. And in fact, it is typically a coextra group of type dn/2. I forgot to say here n should be even. And this is also something that appeared in Sarah's talk yesterday, because what is dn/2? It's the intersection of AN with the group of sign permutations that we talked about, I mean, mentioned in a brief, because someone asked, maybe it was not the center of the talk. So dn/2 is all even permutation that preserve this graph structure. So it's the sign permutation group, the even permutation inside the sign. There are other models of randomicity. Let me be very brief here. So one model is the restricted coefficient model that, for example, we take the coefficient to be 0, 1 at random, and we let the degree grow to infinity. This model is much more difficult, and we know much less. We don't even know the equivalent of van der Waerden theorem. We don't know, even under GRH, although there was a lot of progress done recently, we don't know that the probability for the Galois group to be AN goes to 0. And this is completely, has nothing to do with Galois group. We don't know that if you plug in the discriminant polynomial of degree n 0, 1 at random, that almost always it's not a square. And this is still open. And there are other models that came in recently of random matrices. In these models, you don't choose the coefficient independent, you choose the matrix according to some kind of ensemble. So Eberhard choose the matrices to be with 0, 1 entries independently, and you take F to be the characteristic polynomial. And then you can do some things, but still, yeah. So this is just to give you some feeling, and Ferber, James, Sainz, Sawani consider the symmetric matrices case of Eberhard version. So just to give you a feeling that even if we knew everything in the large box model, which we don't, we know very little, there are slightly more complicated models that we still don't know anything. So if you want to work on it, there are a lot of things to do. And let me just finish by summarizing the talk and tell you why I think that we don't, why I think that the inverse Galois problem is so difficult. I think if you know this story, because we can only look under the light, and under the light all the groups are SM. You don't know this story, but no. Thank you very much.
Are there any questions or comments for Lior?
Yeah. So if you take, as you know, if you take a let's say a Zariski dense subgroup of, let's say, a symplectic group or some other, you will typically get a characteristic polynomial which has a Weil group as a Galois group. Do you know, or have you looked at the distribution of smaller groups in that situation where we know the generic case is the Weil group, but well, what could be the other thing that happened? Would it be different or would it be the same?
I don't know. I think so. Yeah. So if you take some kind of other families like the characteristic polynomial of, then I don't know if what to expect to be the second most probable group. I mean, or the more interesting question in my eyes, what will be the next transitive group? No, I don't know, and I didn't see a lot of research on that. So I a little bit looked on it, and it's very difficult in my eyes.
Can you guess the probability of a discriminant being a square?
Yeah, I believe that it should be h to the minus n over 2. But and this kind of, for me, it gives some very weak how to say, evidence for that, because I found that the discriminant being the square is h to the minus n over 2 minus a half. But I don't have any good reason to believe, because the best result, the best upper bound is h to the minus 1. And it took almost 100 years to get to it. So there is a huge gap between what I believe and what is known. And there is no good heuristic or numerical evidence for either.
The two constructions you had for lower bounds, they both feel like the sort of a simple case of something geometric. You're forcing pairs of roots to come together,
Right.
which suggests one could count in a Bhargava type way. How often that happens?
Yeah. So the second thing was very geometric in the sense that whenever you have coextra group, you have the theory of invariance of coextra group, and this gives you a polynomial, and then you can count by height. So you can apply to other groups like the exceptional groups. And
no, I guess I was thinking that, you know, typically you'd expect a square to have a largest prime factor, be a power of h.
Mm-hmm.
So then one could start examining when modulo p squared, when p is a power of h, do you get, you know, locally roots coming together?
Yeah.
I don't know if that's.
Yeah, I understand this. I need to think about it, but I'm not sure that it will work because it was something very specific to primitive. But it's so you change modulo p and you get something doesn't change modulo p squared, and this gives you extra saving. Yeah, it's a good.
I mean, it just, you know, it would be interesting to classify when the discriminant's a square. It may well be that there's some geometric structure that might make the problem tractable. I don't know.
Yeah. Yeah, it's. I hope so.
Any other questions for Lior? Let's thank him again, and we'll